When we talk about information loss in physics, it's easy to imagine something dramatic, information being erased, destroyed, or wiped from existence. But most of the time, that is not what actually happens. In many cases, information is not destroyed at all. It is hidden. Understanding the difference between destruction and inaccessibility is essential for understanding black holes, chaotic systems, and the limits of observation. Information can stop being useful without stopping being real. To see how this works, consider what it means for information to be accessible. Information is only meaningful if it can influence future events. If it cannot affect anything else, if it cannot be retrieved, measured, or correlated with later outcomes, then from a physical standpoint it is effectively gone, even if it still exists in some abstract sense. Black holes make this distinction unavoidable. When matter falls into a black hole, it crosses an event horizon. From that moment on, it can no longer send signals back to the outside universe. Whatever information it carried becomes causally disconnected from external observers. This does not necessarily mean the information is destroyed. It means it has become inaccessible. This difference matters because physics is concerned with what can be tested and connected, not with what might exist beyond reach. Modern physics strongly suggests that black holes do not destroy information outright. Instead, the information becomes scrambled. Scrambling means that information is spread across a system in such a complex and distributed way that reconstructing it becomes effectively impossible. In a black hole, this scrambling happens extremely fast. Any information that falls in is rapidly mixed with everything else inside, losing its original identity. From the outside, the black hole quickly forgets the details of what formed it. Only a few global properties remain observable, such as mass, charge, and angular momentum. The detailed information hasn't vanished. It has been transformed into correlations that are no longer accessible. This is not unique to black holes. Chaotic systems do the same thing. In a chaotic system, tiny differences in initial conditions grow exponentially. Over time, the information needed to reconstruct the past becomes spread across so many degrees of freedom that recovery is physically impossible. The information still exists in principle, but no process can gather it back together. Scrambling is a form of hiding. This helps resolve a common misunderstanding. When we say information is lost, we often mean that it is no longer available in a usable form. We do not mean that the universe has violated its own rules by deleting information entirely. The universe is extremely good at hiding information without erasing it. This distinction also explains why black holes are not special exceptions to physics. They are extreme examples of a general rule. Information becomes inaccessible when it crosses causal boundaries or is dispersed beyond recovery. From the outside, a black hole acts like an information sink, but not because it destroys information. It is because the information is no longer part of the external causal network. This leads to a subtle but powerful idea. Information can exist without participating in the future. Once information is hidden behind a horizon or scrambled beyond recovery, it stops shaping what comes next. It no longer constrains outcomes. It no longer leaves accessible records. From the standpoint of physics, that is what loss means. This also clarifies why debates about information destruction are often confused. They mix two different questions: whether information exists in some global sense, and whether it can be accessed or influence future events. Physics primarily cares about the second question. Hidden information is not useful information. The same principle applies to memory more broadly. Records exist only as long as they can be accessed. Once access is lost through entropy, horizons, or scrambling, the information might as well not exist for anything that follows. This does not mean the universe is careless with information. It means the universe prioritizes consistency over recoverability. Information does not need to be preserved in a readable form forever. It only needs to obey the rules while it remains accessible. Once it is no longer part of causal exchange, physics moves on. Understanding this helps dissolve many apparent paradoxes. Information doesn't disappear in a puff of smoke. It fades into inaccessibility. It becomes background. It becomes irrelevant. The universe does not erase information. It hides it behind limits. And those limits are what make time, memory, and knowledge possible in the first place. My name is Charles Carroll. Thanks for taking the time to listen.